In this section now we'll talk about the solutions to the time-independent Schrödinger equation for the rotational Hamiltonian, or for the rigid rotator model, and these are known as the spherical harmonics. So the spherical harmonics are worthy of their own separate discussion because they come up all over the place anytime you try to expand central potential in terms of angular momentum. And so these are very important, and they are used constantly in computational physics and chemistry. Okay, so the spherical harmonics are normally written using the symbol y, and they contain two different quantum numbers. And we'll talk in a second about what those mean. So it's y of m and j, and then it's a function of theta and phi. Okay, and the general structure looks like this. And this ranges from j equal to 0, 1, 2, etc., and m equal to minus j plus 1 up to 0, and then on past to j. Okay, so now let's talk about each of these terms separately. So this first part up here, this is just a sign convention, really. So this I to some power will just be a factor that goes out front, and this is really just based on convention. Next we have this nj sub m. So the nmj is just a normalization constant, which is given by the following. So all of this and then square root. Okay, and this is just here to enforce that the ymj is normalized. So the integral over all space of the spherical harmonic, or actually this integral over the solid angle of the spherical harmonic, is 1. The next piece is this function of p, where you notice that the argument to this function of p is cosine of theta. pj absolute value of m of x, right, putting in x instead of cosine of theta for a second. This is a special polynomial called the associated Legendre function. This is another one of these special polynomials, just like what we saw with the Hermite polynomials, although this one is now named after the Legendre polynomials. So we are not going to go through a detailed derivation of what these look like, but I will give you some examples, and there's a pretty decent introduction to this in the textbook, and so I recommend that you go and take a look at that for more information. And then the final little bit is just this phase factor as a function of phi. So this e to the I m phi, so this is just basically a phase factor that depends on the azimuthal angle. And so this will end up encoding the, as we'll see in a second, this will end up encoding the LZ angular momentum. Now, there are several very important properties of spherical harmonics that I'm going to introduce really quickly that are worth remembering or worth keeping in mind. So the first is that these Legendre, the associated Legendre functions, this thing will equal 0 if the absolute value of m is greater than j. Remember, so j starts from 0 and upward, and then these special functions end up being identically 0 if the absolute value of the number in the upper argument is greater than j. And this is the reason why we end up with this condition over here, where the m can only go from minus j up to j, right? So the m must be an integer, j must be an integer, and this is a reflection of the fact that the absolute value of m must be less than or equal to j. Or in other words, allowed values of m go from minus j to 0 up to j. And if you add up all these different allowed values, this is what tells you that your degeneracy of this state, or the degeneracy of your j values, is equal to 2j plus 1. Because there are, if you count from 1 to j, there are j terms there. If you count from minus 1 to minus j, there are another j, and then you have the 0 term. And so there are 2j plus 1 different values of m that give you distinct Legendre, associated Legendre functions, and that define non-zero spherical harmonics up here. Okay, so the next fact that's important about spherical harmonics is that the spherical harmonics are eigenfunctions of both L squared, which is what we were originally looking for. This is, L squared is proportional to the rotational Hamiltonian, and so this is what we need. But also they're eigenkets of Lz. And in fact, this is why this has two different quantum numbers. Okay, so the way this works is that if you apply Lz onto ymj, and this is still a function of theta and phi, then the result that you get is h bar times m ymj theta phi. Okay, so what this means is that the m value that you get up here is in fact related to the eigenvalue of the Lz operator for this spherical harmonic. Similarly, if you apply L squared onto the spherical harmonic ymj, what you get should be h bar squared times j plus 1. And this is what we saw for the rotational Hamiltonian as well, right? So our eigenenergies ended up looking like this, divided by 2i, because the Hamiltonian was L squared over 2i. And there's a ymj theta phi here. Okay, so what this tells you is that ymj is an eigenfunction of the Lz operator with eigenvalue h bar times m. At the same time, ymj is also an eigenfunction of the L squared operator with eigenvalue h squared times j plus 1. This setup is possible purely because the operator for L squared and Lz commute, right? So this commutator is 0. In fact, the commutator for any single direction, the commutator of L squared with Lx is also 0, and the commutator of L squared with Ly is also 0. But no two independent directions commute. Right? So this commutator of Lx with Ly is not 0. The commutator of Ly with Lz is not 0, and the commutator of Lz with Lx is not 0. Okay, so what this means is that the spherical harmonics are a particular choice of the eigenfunctions of L squared that are also the eigenfunctions of Lz. And you could equally well have decided to set things up so that what you have are eigenfunctions of L squared and Lx, or to simultaneously have eigenfunctions of L squared and Ly. But you cannot have eigenfunctions of all of these three, or any two of these in fact, at the same time. So it's because L squared commutes with any one of these, but none of the Lx, y, or z commute with each other. Okay, so and this is why this is a special choice, where the spherical harmonic is a special choice in which the functions are simultaneously eigenstates of Lz with eigenvalues h bar m and L squared with eigenvalues h squared j times j plus 1. Okay, when we write these in Brock-Het notation, we'll typically write them like this. So we'll write them out using their two eigenvalues, or their two quantum numbers, j, m. And so this would correspond to the spherical harmonic of j and m. But next, let's take a look at the first few spherical harmonics and see what they look like. So before we focus too much on this, I want to alert you to the key over here that will tell you how to interpret these. Okay, so these are polar plots. So what these plots are all showing are the magnitude of the y jm's. So here, this plot is using ylm. So it's slightly different notation from a different book, but it's the same exact thing. And what these plots are showing you are the surfaces that are borne out by scanning theta and phi, and then drawing a surface at the value of yjm's magnitude squared. And so what this is doing is it's basically getting rid of these phase factors, but it's showing you the overall shape of what these things look like. Or, to put another way, it's showing you where the different lobes of this end up getting focused. First, you have the j equals 0, m equals 0. So this is written with L, but let's just ignore this and write j for our sakes. So the first spherical harmonic here, using j equals 0, has actually no theta or phi dependence. So this is perfectly spherical. It's the same value everywhere. And so because we can do this integration easily in our heads, or maybe we know already that this integrating 1 over the solid angle gives you 4 pi, so that makes sense that this normalization here would be 1 over 4 pi. And so when you draw this out in this polar plot, it's all of the points that are exactly 1 over 4 pi away from the origin, which is a sphere of radius 1 over 4 pi centered at the origin here. Okay, so this is the j equals 0, m equals 0 case. Now, when we go to j equals 1, we have two different types of solutions. So we'll have the j equals 1, m equals 0 case. So this is this is what's shown here. And you see going up and down along the z-axis for the m equals 0 state. Whereas for the m equals plus and minus 1 state, you have this almost quite donut shape, right? Where now it's sort of flat and squat in the xy plane. And it doesn't have this great big dip, or it doesn't have this great elongation. And so here, this might sort of make you think the j equals 1, m equals 0 might make you think this looks quite a bit like a pz orbital, maybe. And that might make some sense, and that's in fact correct. But then when you look over at the j equals 1, m equals plus and minus 1 plot, this probably doesn't look much like anything to you, right? So this does not really look like a px or a py. And the reason for that is that the normal px and py that we are used to thinking about are actually what are known as real spherical harmonics. And we'll talk about those in a second. But the major point is that those are actually included inside of here. It's just that this is a particular way of looking at it that makes it a little less obvious. Okay, so now you notice that, so these things have cosine thetas, and then they have, so y1 minus 1 and y1 plus 1. For one, they have these different sign conventions, and again, this is just pure convention. And this is also, you have plus I and minus I, but everything else is the same. So you have a different sign, the prefactor is the same, the polynomial or the associated function is the same. They just have this different phase factor up here. And then finally down here, what you have is the j equals 2 levels. And now in a similar way, this j equals 2, m equals 0 might, like there's no coloring, so there's no phase information, but it might make you kind of think about a dz squared orbital, right? So now we're in the d orbitals, which have these shapes over here. But again, of the same token, this j equals 1 or j equals 2, m equals plus and minus 1 has this weird shape that I'm not really sure how you would describe. And once again, the j equals 2, m equals plus and minus 2 has almost like a donut shape. It wouldn't be a donut because there wouldn't be a hole in there, but it would be close enough. Okay, and these are the actual forms, and again you see how y of j equals 2 with m equals minus 1 and plus 1 again have the same prefactors and the same associated Legendre function, but the sign, there's this weird sign convention, and the phase factor out here is different. And similarly, if you look at the y of j equals 2 and then m equals minus 2 and plus 2, then again, the normalization constant's the same, the associated Legendre function's the same. In this particular case, there's no weird sign convention, so these both have the same sign. And now there's the e to the I2 phi just changes sign here. Okay, so now the last thing we're going to talk about, which will hopefully connect this better to things that you've known, is how to transform these into real functions, no longer complex functions, that look a little bit more like something that we're used to. And so the basic idea is that you can take linear combinations of two different spherical harmonics with the same j and the same magnitude of m and produce a real spherical harmonic. So I'll give you an example. So if you take the definition of y1, 1 and y1 minus 1 that we saw on a second ago, and we take this particular linear combination, so we take y11 minus y1 minus 1, then we can just substitute in the definitions that we gave before and that are in the book. Okay, remember they both have the same factor out front and they both have the same associated Legendre function, which is this sine theta. But where they differ is in the phase factor and in the sign convention. So when we put these together, we say these are equal to e to the I phi plus e to the minus I phi. Okay, but now this is something that we've seen over and over again, and hopefully some bells are ringing in your head, which tell you that this thing here is equal to 2 times the cosine of phi. So if we push this a step further, this will turn into square root of 3 over 4 pi, because there's a factor of 2 in here, and when you bring this inside, that simplifies the 16 to 4 pi, times sine theta cosine phi. So first off, this is now a purely real function. There's no e to the I or anything like that in this. But the next thing that's really important is that we can actually simplify this even further into functions that we're used to thinking about. So if we remember for a second the definition of the x variable in spherical coordinates, we wrote in spherical coordinates that x is equal to r times sine theta times cosine phi. So by comparing this with what we have up here, we can immediately see that this the sine theta cosine phi that we have up here is actually just x divided by r. Okay, so this shows you that taking a linear combination of the y11 spherical harmonic and the y1 minus 1 spherical harmonics results in something that is not only purely real, but it also is a lot easier to interpret because this now points purely in the x direction, and this actually will end up looking something like a px orbital, or it will at least contain the angular part of the px orbital, which is something that we're used to thinking about. So I want to show you some examples of what this looks like. Okay, so now these are two very similar plots to what we saw just a second ago, where the distance away from the origin encodes the magnitude of each of the spherical harmonics. But now on the left, it's complicated a little bit because now we're color coding based on the angle in the e to the I. And so more or less what you can think of we're doing, e to the I m phi, you can think of m phi as an angle, and then you just color the surface depending on the value of this angle. And so if we look over here at the left, this is the equivalent of our y1, 1 function. And so we notice that the angle goes, or that this color just goes around kind of like a color wheel that's been expanded up into something that looks a little bit like a donut. Okay, so now this is the same information content as before, but we're really just color coding the surface of these in order to show what's going on with this complex angle up here. So if you go down these, you notice so this is the y11, here you have the y22, and here you'd have the y33. And so one thing you should notice is that this ends up going, this rotation or this color wheel ends up getting compressed as you go down this line, right? So here, there's this one sort of teal band back there, and you only recover that teal band when you get all the way back to the front. For y22, there's this little teal band here, and there's another one here, and then you get back, and so this goes through this whole thing twice, which makes sense because here this is e to the I phi, and for the y22, it's e to the 2 I phi. And then, as you can imagine, for y33, you start off with, you see 3 of these repetitive bands, because down here you have e to the 3 I phi. Okay, now just like we did in this example of here, where we take a particular linear combination of these two functions, we can make something that is both real and point in a particular direction. Now, if we take linear combinations of these complex spherical harmonics on the left, we can end up with real spherical harmonics on the right, and now these do look exactly like the normal px, py, and pz type functions that we're used to. Again, so these are still different because this is only the angular part, and the actual px, py, pz orbitals also have a radial part, but still this is suggestive enough that you can start to immediately see how you can take these, flattened disks for the y22, and then from these here you end up with these two distinct functions. These would be like the dx squared minus y squared and dxy. And then the same thing works even beyond for these f orbitals, although these are things that normally we don't spend a lot of time looking at because they are a lot harder to draw by hand. One extra point I'd like to make about the real spherical harmonics in contrast to the normal spherical harmonics is that the real spherical harmonics are no longer eigenfunctions of Lz. So what you've done here is you've taken a linear combination of two functions with different eigenvalues of Lz, so different m values. And so because you have a linear combination of two different functions with different eigenvalues of Lz, the result over here is no longer an eigenfunction of Lz. And so this is the trade-off. You get something that's much simpler, that's no longer complex, so you don't have to handle complex numbers, but you lose a quantum number. And so now the result is now an eigenfunction of L squared, but no longer an eigenfunction of Lz. Okay, so this is all that we're going to worry about the spherical harmonics for now, either the complex or the real. They will come up again, I promise you, when we start talking about the hydrogen atom and the solutions to the time-independent Schrodinger equation for the hydrogen atom. And they're also an endlessly fascinating subject that tend to pop up all over the place in all sorts of different problems. Anytime having any sort of a spherical expansion is useful, which tends to be very frequently. This was not a particularly thorough discussion of the spherical harmonics and all of their intricacies. However, the one in the book is a little bit more detailed, and so I highly recommend you go and look at that